gas, and you can change its volume. Okay, so put your coloring devices away, earphones out, 1 through 16, ready? I'm going to start with number 10 and 12, and I'll backtrack to 15 and 16 as some people ask. So I just want to get you started on 10. I'm going to do student A. Those of you who are absent today, we did about 30 minutes of the gas laws foldable, and you can see all this stuff on here. That's what we're doing. Okay, have fun. And here we go. Student A for the number 10 is what I'm starting with. They were told that, or you were told that student A collected 5 liters and 5 liters of gas at 25 degrees Celsius, which is 298 Kelvin. That's information about student 1. Student 2 had 4.85 liters of gas at 22 degrees Celsius, which we would then convert to Kelvin, which would be what? Say again? 295 Kelvin. And then it said the theoretical yield for the gas at STP is 4.97. Notice that these two people are not at STP. What are the conditions at STP? What's ST? What's standard temperature? 273 Kelvin. And what's standard pressure? So 1 atmosphere, which is equal to 760 millimeters of mercury, which is equal to 101.3 kilopascals. Any of those will work. So those are the conditions that they're comparing to. Well, if these people, students A and B, are not at those conditions, we need to get them there before we can find their percent yield. So that's what I've just only done on student A. This was their initial conditions. We need to compare that to STP conditions before we can compare their volume of gases made to the theoretical yield of 4.97. So their volume is what we're looking for. They got 5 liters at 25 degrees Celsius. Well, what would their volume be at 273? Because that's what we need to compare to. So at 273, the way I've set up is V. I did Charles' law, V1 over T1 equals V2 over T2. So I solve for V2 by doing V1 over T1, and then I multiply by T2 on the other side. So this is our rearranged formula. So we're solving for V2. 5 liters was what they got at 298. So when we multiply by the 273 Kelvin for its standard conditions, the volume is, what is this? Anybody? 5 times 273 divided by 298. Oh, fractions. 4.58 liters. And that's what their gas is equivalent to at STP. So that's their volume. That's their actual yield. So how would I get their percent yield? Remember what percent yield is? 1. That's error. You're minusing, that's error. That's difference. So it's just actual over theoretical times 100, right? So actual was 4.58. Theoretical was what should have been happening was 4.97. So student A had 4.58 liters actual yield over 4.97 liters theoretical yield times 100. Somebody tell me their percent yield. 92%? Okay. And then you will do that same thing for student B. I'm not going to set up student B's though. You guys can just set up student B's. So all you're doing is just converting with Charles' law. That's why I was in the Charles' law section. To their actual yield, not their actual yield, but their actual yield. Do you know the difference? Their actual yield is what they got at their temperature. Their actual yield is what was converted to STP. So that's how you set up number 10. That was a little hard. 12 was weird the way it was phrased. Now I've read it again, and I can see now why you guys were like, what? So 12, when it said calculate the temperature of nitrogen gas is 2 liters. That's saying if it's about 2 liters. So the question is asking for temperature. We all know we're looking for a temperature. But then you have to figure out which was 1, which was 2. Well, I want you to look. Does it say that the volume is changing? It doesn't. That's why it's under the Gay-Lussac, because we all assume that volume is constant. It says it's 2 liters, but is that information really all that important? No, and that's the hard part, because you're like, where do I put this 2 liters? You actually don't need to use it at all. It says that the 2 liters is there, because it's talking about a volume of gas, but that is not changing. It's irrelevant. Cross it out. So then you're easy. I think you guys can get it from there. It says to calculate the temperature of a gas. That's at STP. Okay, so at STP is our temperature and pressure, and that's a combined one. And I just selected that to be T2 and P2. You could have made that the ones, and that's fine. But that's 273 and then 760 millimeters of mercury, and I chose that one because my other pressure they gave me was 920 millimeters of mercury, and the mercury units need to be the same. And so at that point in time, I know that my temperature and my pressure, the unknown temperature and the pressure given, they're of one scenario, and so I make them the P1 and T1. And then the STP are a combined scenario, so they're the T2s and P2s. So then, do your bow tie method, solve for T1 by cross-multiply division, and T1 will equal P1, which is 920, times your T2 over your P2, and give you T1 is equal to 330 Kelvin. And in my answers, sometimes I'll put them in Celsius because I want you to get Kelvin, and I want you to convert back to Celsius. Only because if I put Celsius in the answer key, you might accidentally use Celsius in your problem. And I want you to always remember, you're always using Kelvin, but sometimes it'll say, what's the temperature in Celsius? So just don't forget you have to convert back. Okay, so that's 10 and 12, and that's what I saw a lot of people were a little bit confused on. 15 and 16, I also heard some confusion, but it's just combined gas law. And you set up all your PV over T equals PV over T, and all your units need to be equal. So if it's pressure in millimeters of mercury in one of them, it's got to be millimeters of mercury in the other one. I think more than anything, you just didn't realize that STP was giving you 2 data points. Do you know that now? STP gives you pressure of 760 millimeters of mercury and temperature of 273. So those will be your other conditions. So I'm not going to do those 2 right now, only because I want to make sure we get to ideal gas law. So let's look at ideal gas law. Before I jump into that, I want you guys to sketch out pressure containers. They're weird. We'll do our simulation later. It's okay. Ooh, who knows what this is? What is this fancy device? Can you see it? What measures pressure? That is a barometer. It's kind of hard to see. There's mercury in here. So the way it works, there's mercury right here, okay? There's all mercury right here. Okay, there's the mercury in red. So what happens is air pressure has to push on the mercury. And literally the millimeters of mercury they measure are literal millimeters. You see the little hash marks here on a ruler, basically? Those are really millimeters of mercury. That's where that unit of pressure came from. It wasn't like, let's just call it millimeters of mercury. They're literally measuring a length of, or a height of mercury. So there's like actually an open end here and on this side, really, because you want atmospheric pressure coming from both sides. So the pressure of the atmosphere is pushing inside of this tube, and the air pressure is just everywhere, right? Well, we've got it coming in from 2 ends. But the air pressure pushes on this air, and this is just air right here. Air, and it pushes against that mercury level. And so if the air pressure is really high and it pushes a lot, what does it do to the mercury height? Huh? It's going to push it up and it's going to make it higher. Well, and if you read a higher height, doesn't your millimeters of mercury go up? Yeah, so that's how they can say the pressure is high. It's 780 millimeters of mercury. The top number up here is 800. And so it would go off the charts past that. But what if we were on top of a mountain and we had our fancy barometer? So then what would this black pressure right here look like? The air pressure over here. Would it be would it push the mercury this way or let it come back this way? It would let it come back because the pressure here would be less. So the mercury would not be pushed as far, so it would dip back and maybe even come back on this side some. And up here, it would lower, and so then the pressure reading might be like 700 millimeters of mercury. And that's actually what they use before they have different devices that are not as ancient as this. Okay, so our pressure systems, we don't use mercury because it's toxic. We use water. Okay, so here's how we actually will be using water measurements in the lab. So let's go with the one we're going to do tomorrow. Are we doing this tomorrow? Yeah, I think we are. Because you guys need to learn about how to read. An upside down graduated cylinder. Look at that baby. You see it? That's the graduated cylinder. Okay, draw yourself a beaker and a graduated cylinder. This is our fancy barometer. Talk about engineering, right? Make it happen. So what we have in our picture here is a beaker filled with water. And I'm going to put water in blue. And the water goes all the way into the neck of the graduated cylinder that's inverted. What's outside of the water? What's outside the water? Air. Simply air. Well, what's the air doing to the water? Pushing down on it. It's air pressure, right? So I'm going to put P of atmosphere out here. And I'll even put it on both sides because, you know, it's everywhere. We know it's everywhere. We saw it push the egg into the bottle. So the air pressure pushes on the water on both sides. Well, this pink stuff in here, what we're going to do is we're going to hold a lighter, like a butane lighter underwater. We're going to light it underwater, and the air that's made from the combustion is going to go up into the graduated cylinder, or it just might be non-combusted. But regardless, this pink stuff up here is air, not air. It's a gas. But our gases will differ based on how we get the gas in there. So this pink stuff is gas. Well, you can see that there's just gas everywhere in here. Well, what's the gas doing? Where's it pushing? Down. It's pushing down onto this little surface where the water meets it. So if the gas is pushing on the water, and the water, which is being pushed by the pressure of the atmosphere, of course, the water is pushing up on the air. Get all some green for you guys. Okay, the water's pushing up on the air, but nobody's winning. What can you assume about their pressures? They're equal. Do you all realize that? If there's no water being pushed up into the gas and no gas being pushed down into the water, they're equal. So the way I've drawn it so far is pressure of the atmosphere is equal to pressure of the gas, whatever the gas is that we're talking about that we've collected from our experiment. So tell me what would happen if the pressure of the atmosphere was greater than the pressure of the gas. So the pressure of the atmosphere would push the water from its container into the graduated cylinder. So we would have something like this. So has everybody drawn this little part here? I'm just going to adjust from here, okay? So we would have water moving up. And so that second scenario was pressure of the atmosphere is greater than pressure of the gas. We can see the gas is losing because it's being pushed against its battlefront. Okay, what would happen if the pressure of the gas was greater? So we would push the water back down to the beaker and maybe even out of the beaker on the sides because the pressure of the atmosphere wouldn't be holding the water in anymore. So it's really easy to manipulate it from your initial when everything's equal. But if the pressure of the atmosphere is less than the pressure of the gas, or the gas is greater, as we said, it would push the water out of the beaker, and we'd have it full of water right here. Because that pink stuff would be down into the below the surface of the water. Okay, so similar situation. This is a flask. You see it? Squint your eyes, turn your head to the side. Triangle, it's a flask. Got it? Okay, I couldn't draw a flask very well. So we have a flask here. And we have an open, this is called a U-tube. Okay, it's called a U-tube. So the U-tube is connected to the flask over here and with a closed end over here. Well, this flask got some crazy reaction going on in it, right? So the crazy reaction is making a gas. Here's our gas, P gas. And P gas is just in our flask, and it's pushing because it's everywhere over here too. Well, P of the atmosphere is open to is exposed to the open end of the U-tube. So P of the atmosphere is pushing on this. This is mercury or water or some sort of liquid, okay? P of the atmosphere is pushing on this side of the U-tube. P of the gas is pushing on this end of the U-tube. What can you deduce right now? They're equal because nobody's on the U-tube pushing up or down. They're equal. So what would it look like if P of the gas was greater? Because right now P of the atmosphere is equal to P of the gas. What would it look like if P of the gas was greater? So the height of the mercury would be greater on this side. Okay, so you're saying, I don't have pink. Okay, you would say it's like here, right? Okay, well, so you're saying P of the atmosphere is less than P of the gas. Now I want to quantify it. I want to say how much greater is it? If this pink stuff is mercury, okay, what you're going to do is say, okay, the height of the gas is here. The difference is in the height, right? The difference is that. So I'm going to call that change in H, change in height. So if it's mercury, how do I want to measure the mercury? In millimeters. So hold up a ruler, really, just hold up a ruler, and I measure. Oh, that's like 10 millimeters of mercury different. So what's standard atmospheric pressure again? 1 or 4 in atmosphere, and 1 in atmosphere is about 716 millimeters of mercury. So the P of the atmosphere is supposed to be 760 millimeters of mercury. And we're saying the gas is pushing it back by a difference of 10 millimeters. What's truly the pressure of the atmosphere? So what, are you guys adding 10 or minusing? Yeah, so you're subtracting, so you're saying it's less than what we think it is, so you're subtracting 10 millimeters of mercury, so it's actually 750 millimeters of mercury in this example here. So what if it were the other way? What if the height had differed here by 10 millimeters of mercury? What would be the atmospheric pressure? 770, because it's stronger than what it would is that equals. So it's stronger by 10 millimeters, and so you increase it and say the atmosphere is 10. So then what would the gas be? So if in this case, not in this case, in the one I just said, if you said the atmosphere was stronger and you said it was stronger by 10 degrees, 10 millimeters of mercury, you said the P of the atmosphere is 770 millimeters of mercury, what would be the P of the gas? 750, because it would be 10 less than what equal was. Equal was 760, 760, so the P of the gas would be 10 less, which would be 750 millimeters of mercury. So I just want you to be comfortable looking at these diagrams and saying this is stronger, and if we can measure a height, we will, and just say by how much. But really, more than anything, we're doing that thing tomorrow, okay? We're flipping that graduate cylinder upside down and measuring it. So that's what we're going to be using for our barometer. Okay, and this is kind of the differences in height, too. You can see how this works. Pressure of the atmosphere is 760. It's stronger because it's pushing like this. This is into this is in a round bottom flask, not a Erlenmeyer flask. And the difference here in height, you can imagine, is what? According to the math here. Oh, it's right here. Sorry. It's 50 because you're subtracting the height. So you're subtracting whatever this is, and you get 710. So 760 minus something is 710. So the height is 50 millimeters of mercury. Okay, I think we're okay there. Let's skip the rest of these drawings. We did that yesterday. Okay, fantastic. Woo! Let me get past this. We'll come back to this. We'll come back. Ideal gas law. Ready. So I'm going to explain to you a little bit about what the KMT is, and then I'll backtrack. This is something that you read a little bit about in your reading at 14. When I say read about, you should look at your book some. In college, you will have to read that textbook probably from cover to cover. So you want to get used to reading scientific language through a textbook. Your teachers will teach. Some of them will teach very little. Some of them will go above and beyond. I have one professor right now that, like, she does everything under the sun. She videos her notes. She puts annotated notes online. She gives us practice quizzes for extra credit. We read the book. We attend office hours. Everything. She is, like, literally awesome. And she just got a new book, so she just has to do everything to correlate her book. I have another professor who does nothing. And I'm like, am I paying you to teach? And I'm getting a degree, but I don't know much. I'm just reading a book, and that's all I'm reading. So I literally have to learn everything from the book. So it's a little different. So that's what I'm saying. You should read your book for your kinetic molecular theory. But let's talk a little bit about that. Kinetic molecular theory. What do you think the term kinetic is referring to? Kinetic energy. And we talked a little bit already about how kinetic energy relates to gases. Tell me about how kinetic energy relates to gases. Oh, Niall. What do we know about kinetic energy?
The gases with the highest, like the molecule of the gas with the highest kinetic energy.
Any state of matter, right? So if I'm a gas, how do I get more kinetic energy? Increase the temperature. So we all remember kinetic energy is related to temperature. It's actually average kinetic energy is equal to temperature. Because some particles move very, very fast, while some move a little bit slower, but the average kinetic energy is related to the temperature, and that will control how fast particles go. The molecular part of things is talking about how the molecules collide with container walls, and that causes pressure. So that's going to be how temperature is coming into play, the pressure part of it's coming into play, and then, of course, if you have more gas, what's going to happen to the pressure? If you have more gas particles bouncing around, what's going to happen to pressure? It's going to go up. So that's where the number of particles are coming into play. So what we're seeing is everything lumped into one equation that's going to be relating all of our facts that we've been learning about. PV equals nRT. Now this is for a one scenario deal. It'll say like, here's the pressure of the gas, here's how many moles of gas I have, here's the temperature at which it lives, and I want you to find the volume. Notice there's no two pressures, two volumes, two temperatures. That's all Gay-Lussac's and Boyle's and Charles's law stuff. This is a one scenario kind of deal. Now this unit here, for R is our constant that we use to relate all of these variables together, is the universal gas law constant. 0.0821 atmosphere liters per mole K. Atmosphere liters per mole K. You must use pressure in atmospheres, volume in liters, moles in moles, okay? Number in moles, and temperature in Kelvin. You cannot use millimeters of mercury. You cannot use Celsius. You cannot use anything else but those units, because I'm going to ask for you to use this R constant for the ideal gas law. So that's what this right here is depicting. And whenever you're using the R constant, you must do that. So let's go ahead and look at number 17 on the questions you guys have started. We're going to do one of the next right now. So this is a scenario where you have one. The answers one problems. Let's do 17. So I want everybody to work through it just like we did yesterday by noting givens first, and then we'll go from there. So looking at 17, a student, this could be you. Okay, a student collects 425 milliliters of oxygen. Stop. What is it giving me? V is 425 milliliters of oxygen gas at a temperature of 24 degrees Celsius and a pressure of 0.889 atmospheres. What's the question? How many moles? So what unit is that asking? I mean, what variable is that asking for? N. It's asking for N. It's nice to know that we're looking for N. Okay. How many moles of oxygen? And when I say oxygen, do I mean diatomic or do I mean just O? I do mean diatomic because we're talking about this reaction. This person's collected a gas and it's a standalone gas. Well, standalone gas is oxygen, and we know oxygen does not exist singly by itself. It exists as a diatomic by itself. Okay, I know diatomic by itself sounds like what oxymoron, but it's like it's not an atom of oxygen, it's a molecule of oxygen. Okay, so it's looking for N, and then later on it says, question, how many grams of oxygen gas is this? Okay, we don't need the question anymore. We have a law in our head. What law is that? It is the ideal gas law. You're like, no crap, that's what we're working with right now. Okay, so I'm labeling them all for you as we go, but in the end, we're going to be mixing them up, and you're going to check it for the law that goes along with the variables given. So PV equals RT. Where's our R? Okay, so it's in our head there, right? 0.0821 atmospheres, liters. That's all a numerator. Per mole times K, and that's a denominator. So make sure if you don't want to write your units on top and bottom, make sure you put numerator and denominator. So then let's go ahead and solve. What unit are we solving for? Or what variable? N. So I'm going to divide by what? RT on both sides. So then N for oxygen, sometimes it's even nice to label what you're solving for because you'll forget. N is equal to PV over RT. Now, before I plug in, can you tell me what variables need to be and change into appropriate units? Okay, so I hear Celsius needs to be changed to Kelvin. Can you go ahead and do that in your head? So 273 plus 24 is 297 Kelvin. What else? Volume needs to be changed into liters. So how many liters is that? 0.2 or 425 liters. You're bouncing decimal back 3 spaces. You don't need to show me that work. Just put it right next to it, and I've got it. Atmospheres are hunky-dory. We're all good. So plug it in, people. Pressure, 0.889 atmospheres times volume, 0.425 liters. You see I'm putting my units like a good student, because this student could be you, make sure you put your units, are 0.0821 atmosphere times liters per mole. Okay, so this is like a fraction in the denominator. And then temperature 297 Kelvin. Before we move on, let's cancel units. I want to make sure you understand what's a numerator, what's a denominator, and what's cancelable. What do you think cancel? Okay, so you see atmospheres in the numerator and in the numerator the denominator. But it's just the denominator. Okay, so atmospheres can cancel. What else? Liters on top and bottom can cancel. And so this is Kelvin and the numerator of the denominator. Okay? This is Kelvin and the denominator of the denominator. Still, it's a numerator and denominator combo. Cancel. So this mole that's in the denominator of the denominator actually can, do you guys remember how it's like if you have something, that's a Y, and that's a Z, and that's an A. If you have something on two fractions, you guys know how to copy dot plot. There it is. Okay. So that's basically how that mole gets back on top, because the mole is not going to be in our denominator anymore. It's going to be like you multiplying by copy dot plot. Okay. So then that's how that A gets back up top. Trust me, the mole is remaining. Okay. So the mole is remaining. And our units are going to be in moles. What's our answer? Go ahead and calculate. Because the old parentheses need to be used because you need to have a numerator answer divided by the denominator before you finish your calculation. Got me, James?
Yeah.
Compare with Lindsay before you tell me. Calculator. Got your calculators. Where'd you guys go?
0.14. It's like 10154.
0.0155 then, right? So please make sure you put that in your calculator correct because you get this. This is good. And this is talking about oxygen gas. Answer 1, done. All we did was solve for N from P equals nRT. Now, I need to see how much gas this person collected in terms of mass. So what do I need to do as my last step? Convert to grams how? Timesing by, or using molar mass and a conversion. And this is stoichiometry again. Yay! What goes on top? What's the molar mass of oxygen? Lies 32, because it's diatomic. Don't forget it's got 2. So 32 grams of oxygen per 1 mole of oxygen, diatomic, gives us what? 0.4965, something like that, grams of oxygen. Okay. So our first answer, we solved for N, which was our moles. Second answer, we used molar mass and got to grams of that same thing. Yeah.
Explain how you put that in the
Yes. And that's what I like to make sure people have a chance to plug in a calculator. When I say use a calculator, I literally mean it. You need to put in your calculator something like this. 0.889 times 0.425. That all in parentheses. And then divide by parentheses 0.0821 times 297 in parentheses. Your entire numerator needs to be in a parentheses, and your entire denominator needs to be in parentheses. That way, it doesn't divide and then multiply in the end. Okay, good question. Okay, nope, number 18. Let's do number 18. 18. I need a slide. Okay. Actually, you guys can do 18. You guys do 18, 19. Jump on it. I don't necessarily need to guide you through it. I could. This is like 50-year-old.
Thank you.
Somebody finished with 18? 18? Did you convert to kilopascals? I do have the answers here, so you can check it afterwards. If you guys want to go ahead and write down the answer to 19, I'll write 18 on the board, and then I want to talk about the kinetic molecular theory. So 620 kilopascals. I'm expecting that you are writing down your givens, because that is how you stay organized. There's no need for you to just try to directly plug in until maybe later on you'll get good enough at it first. This is your first exposure, so protect yourself from making mistakes. Write down your givens, write down your formula, rearrange, plug, 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 cancel, cancel, cancel. Moles cancel here, Kelvin on the numerator here and denominator here, and then liters and meters. The only unit left is atmospheres, and that's why I recorded atmospheres first. And then the question asked you for kilopascals, so you can put kilopascals by using your pressure conversions. Thumbs up if you're okay on 18. Okay, so forewarning, tomorrow. Yeah, sorry, we're doing our lab Monday because I waited because we can't do our lab till we finish this. Okay. So tomorrow we're going to be taking together our gas law, our ideal gas law, and our reactions that we used to do that make gases, those like decomposition reactions that make gases. And we're going to actually make the gas through the reaction, and we're going to calculate how much of that original reactant we needed to make X amount of gas. So what I'm saying is we're going to put ideal gas law together with reaction stoichiometry. And then we're going to make, see what kind of products we can make, talk about the decomposition of the reactants. So we're going to start putting that old stuff and this new stuff together. Okay, so before I jump into that, though, I need to finish up our kinetic molecular theory, which I just skipped for a second. Da-da-da. Okay, so somebody tell me, what is a theory? Like, why do we have theories? Yeah.
Like something that we like have evidence for, like explain the natural phenomena.
It explains the natural phenomena. So we observe something, we're like, we need to kind of make this known. We need to say gravity. Okay, gravity's a law. Sorry, I lied. The theory of natural selection. Natural selection occurs. Evolution of species occurs. There's been this observation. Now we have a theory for it. Well, that kinetic molecular theory we just talked about, we made all these observations. You're like, oh, balloons expand when I lower the pressure. Balloons expand when I increase the temperature. So we've seen all these gases. We've seen them do things. So we wanted to put it into a theory. Now the theory is called kinetic molecular theory, right? We know that it explains something. Well, it's explaining the ideal gas law. It's explaining these conditions that gases are at and the behavior they have. Well, ideal. You guys know what ideal means? Yeah, so raise your hand if you think you're my ideal student. You believe you're my... There you go. Participate in class, do your homework, come to chem club, come to lunch with a scientist tomorrow during till A or B. Plug there. Come early, bring me chocolate. What did I say one the other? I didn't show you guys. I showed my here. I want this little Loch Ness Monster ladle. So you guys know what I'm talking about? Look for it on Amazon. Okay, so ideal students, you all are. Okay, so if I think, close your eyes, think of an ideal man or woman. Think about it. Give me some characteristics. Keep it PG. Tall, abs. Okay, so superficial. Okay. Good hair. Good hair. Okay. All right. Smile. Guys. Now you'll smell everything. Nice. Intelligent. Okay, so I'll tell you mine. So my husband is my ideal man. Okay. cry. Met him when I was a sophomore. Okay. He was a junior. Dating an older guy. Okay. So he makes me coffee every day. He let me get a dog without his permission. He did not like it for a long time. So he didn't know, and I just brought the dog home. But he still loves me for it. He takes care of my dog. My dog, you know, she's not real. She chews up his shoes. And only his shoes. Only his. Not mine. She's saying something here. Does really whatever I want him to do. I say, will you drive so I can grade papers? Will you go to this science event with me? We went and saw Neil deGrasse Tyson. We went to this, like, science cafe. Yeah, so he's a real big nerd. He just does whatever I need to do. So, but, you know, he sometimes watches my nice stuff with not so nice stuff, and then it shrinks up my stuff. That's the less ideal part. And then sometimes he gets me on these, like, Netflix binges. It's not good for my health. Okay, so I'm trying to make him stop doing that. So, and he won't go running with me. So it's a sad day. But anyway, so most of our lives, we can find something slightly ideal. But there's always these small parts that just are not 100% ideal, right? So the ideal gas law, do you think there are really ideal gases out there that act perfectly the way we think they should act? No, there's always these extraneous circumstances that are not going to allow them to act 100% ideally. So what do you think we call a gas that's not ideal? Real. We call them real gases because, like, my husband, he's a real guy. He's not ideal. He's a real guy. He's got some flaws. Don't tell him I said that. But he's got some flaws. So what we have are these assumptions about the gas laws. And we assume the gases are going to act one way. But then there's a slight extraneous circumstance we have to consider. And then we go, oh, well, it's not acting ideally. It's acting real. So the 5 bullets here are how we think ideal gases should act. And we assume that. We assume that's how we are able to use the ideal gas law. If we don't assume it, we actually have to use this really, really complex calculation, which even my AP chemistry students are like, what? I don't really feel like doing this calculation. So we just try to assume most of our gases are ideal. We try to assume they mostly follow these rules. 1, ideal gases have no volume. We assume that they're so tiny, their volume is negligible. And that's what it means by insignificant, right? So the volume is negligible. Size of a molecule, so a couple picometers long. Pico is smaller than nano. No, pico smaller? No, nano is smaller than pico. So very, very small. So volume is negligible. But really, is it that small? No. So basically, the ideal statement has no volume. When we say, what do real gases have? They have volume. So they're just counteracting what we've assumed about the ideal. But we really do try to assume everything's ideal because that makes our math easy. We assume that particles are in constant rate of motion, meaning they don't stick together. So no IMFs. So we assume, you know what assuming does, people? We all know that gases really do interact in some way or form. They stick together. That's how gases condense. That's how they go from the gaseous state to the liquid state. We know that happens, but we really try to assume that most of them act ideally and they have that constant random motion. But they do stick. They do collide. They do have some non-random motions where they're stuck together. And it's just because of IMFs, we can't control it. Hydrogen bonding occurs, dipole-dipole occurs, limiting dispersion occurs. So to keep that going with the ideal, we assume that when they collide, they just go bounce off each other. 100% of the kinetic energy is conserved. What can you imagine, though, when they bounce? Have you guys ever seen that Newton's cradle thing? Go like this? Does it slowly lose energy? It slowly, okay, over some time it goes like this. Slowly loses energy. So collisions generally do have some friction. They lose a little kinetic energy, and they slow down. But we try to assume that that doesn't happen so we can use the ideal gas law. So that's why it says elastic collisions. But this one, they do lose energy with collisions. And then we actually did mention this earlier, the kinetic energy component. We assume that the kinetic energy is directly related to its temperature, and that's actually still true. That's 100% true for gas, real gases and our like mythical beast here, our mythical ideal gases. Did we watch Good Mythical Morning? Rhett and Link. They're from North Carolina. I was in California. Stop. They're like YouTube celebrities, okay? All right, so they do have the kinetic energy component is true for both. And then this number, this fifth one, relates directly back to the IMF discussion we had here, so you can relate those. We assume that ideal gases do not like bond up and like, okay, let's stick together. We assume that they actually have no IMFs or no attractions for each other. And or repulsion, because repulsion actually makes them like speed up and then bounce harder off of other things. We try to say they have no interaction, like they don't even know they have other gases around them. But we know that real gases do have attractions and repel. And so thinking about that relationship, if particles attract to each other, let's say I have a container, these are all separate, right? Separate, separate, separate. They bounce off the sides of the container very easily. What if they pair up and they attract to each other? What's going to happen to the pressure in this system? Why? Right. So think of a, what is it? Three-legged race, right? Okay. So single ones, you go, 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 go. People can run freely, bounce off the walls. But a two-legged race, you're trying to bounce off the walls. You're like, okay, let's go. Okay. And you're going to probably slow down a little bit first because you're attracting. And second, you're a double now. So there's less particles that are free to collide. So this pressure would be higher than this pressure because of their attractions. And so it's really hard to account for that in a calculation. Like, who wants to subtract? Oh, it's going to subtract because it's got this much less pressure. That calculation is much more difficult. That's why we assume all these factors so that we can utilize the ideal gas law. And then let's add this part, and I'll finish up tomorrow. The two conditions that can allow for real gases to approach ideal behavior are these. You guys can write that down, but I'm going to write this up in something separately over here. Oh. Okay, so real gases are going to approach ideal behavior when they're under some temperature and some pressure. So let's think, what pressure conditions will allow the gases to run free? High or low pressure? So high pressure goes scrunches them together, like you must interact. So what's going to make them act ideally? Low pressure, and they're free as a bird. There's low pressure conditions. They don't have to touch other gases. Okay, so low pressure conditions means that they're going to act ideally because they don't have to interact. They have a lot of places to bounce around. So what temperature condition means that they're going to freely move and not condense? High temperature. So they're moving really, 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 really fast. Okay, high temperature means they're zooming past each other. They don't have enough time to say hi, much less bond and actually interact. And that's why it's opposite here. Real gases exist at high pressure because they're squished together, and low temperature because they're moving slowly. Okay, so you guys have 2 minutes left. You've got reading that, start at 16. It's not due tomorrow, but please start it. And then that number 19 that I did. Okay? All right. And then I will be here. This is raw for you. This is like the scientist tomorrow. I will be here during today. Today, we need some help with the Contour 16, or if you want to sit and work on 19 with me, or your PS14, okay? Oh, and those are my people who are not going to be here. We're going to do basketball street teaching. That super fun. We'll do the simulation today. Are you going to put a video up? Yeah, I'll video. I will video tomorrow. So you guys will put up like right after class. And then the simulation thing next week. And it can be due Tuesday next week or something. Okay.